So we are moving into chapter 6, and it is a very short chapter. There are 3 sections, and we're only covering 2. So we're going to look at what's that for?
Nothing. I was.
Sighing.
I can't say that. Yeah. Because I don't want to finish it.
Don't say it.
I'm not going to.
All right. So we are talking about discrete random variables. We know what a variable is, right? We see variables all the time. What does discrete mean?
Oh.
Yeah, it has a stopping point. They're countable. So we are looking at countable situations here. We do have a few definitions to get us started. So a random variable is looking at a numerical measure of the outcome from a probability experiment. Okay, so we know what probability is. We've been looking at a lot of those. We've actually done some of these. So we could look at flipping a coin and counting how many heads show up. And my random variable then is the number of heads that we flip. All right, it's discrete because it's countable. I can't have decimal values. You can sit and count how many times you get a heads in them. Continuous, we're not talking about those yet, but those would be infinite values. So it might be having people run a race and looking at their finishing times. Okay, there would be an infinite number of times because we could go to the nearest tenth of a second or hundredth or thousandth and so forth. So that would be more continuous, and we're not ready for those yet. So first we're just going to look at an experiment and say what would be the types of solutions we could have. So we need to make sure we know the difference between discrete and continuous. The number of light bulbs that burn out in a room of 10 light bulbs in the next year.
Discrete.
That's discrete. We can count. All right, so my different options would be what? What could I get at the end?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And we're missing one option.
0.
Right. It could be that none of them burn out, or 1 or 2 or 3, all the way up to 10. So there is a max on that one. B, the number of leaves on a randomly selected oak tree. Discrete. We can count them. Doesn't mean we want to, but we can. So what would be my possible x values? Can we have negatives? Can we have 0?
Yeah.
1, 2, 3. Is there a maximum? No, so that could just keep going. The length of time between calls to 911. That would be continuous. What kind of answers could we get? Any decimal, as long as it's positive, right? So anything, can we just say bigger than 0? We can also make the probability distribution for all of these. We saw some probability distributions in the last chapter, the very first section. So we know the probability distribution lists every possible outcome and the probability of that outcome. And the 2 key components, every probability has to be between 0 and 1, and when you add them all up, it has to equal 1. All right, so let's make a probability distribution. A basketball player is asked to shoot free throws. Create a possible probability distribution for x equals 0, 1, 2, or 3 shots made. Okay, so my x, my probability. So my x options are 0, 1, 2, and 3. Alright, did I tell you how to calculate the probabilities for any of these? No, because I just said make a possible one. So just checking, do you know what a probability distribution is? So you can make up whatever probabilities you want, but I know every one of them has to be between 0 and 1, and when I add them all up, it has to be 1. So what do you want me to put? So I said 0.1, then what would this one have to be? 0.4. Alright, so we just made up some random probabilities there. But the key, it adds up to 1. So I want you guys to take a look at the next slide and decide if those are probability distributions. So take a second on your own. 3 of them, decide if each one is. So is the first one. Why? All right, what about this one? Why? Right, not everything was between 0 and 1. All right, what about this one?
Yes.
Every probability is between 0 and 1, they add up to 1. Are those okay? So let's look at this. So we want to draw a graph of this probability distribution, which represents the number of movies streamed on Netflix each month, and describe the shape. So it didn't really tell me what kind of graph. We could do a bar graph. I'm just going to do a very simple graph here. So I have my x's, which is movies in this case. And my y is my probability. So I'm going to count by 0.1s. And if we go through that, so I had 0, had a probability 0.06. 1 was 0.58. 2 is 0.22. 3 is 0.1. 4.03, 5.01. All right, what are my options when I'm describing shape? We can have symmetric, we can have skewed left and skewed right. All right. And then if I look at this, how would you describe that one? If you think about if you drew in a curve, it's extending off to the right, so this is skewed right. So we can still talk about shape when we're looking at probabilities. Is that okay? So next, this is some kind of a new component. We can find the mean of these discrete probability distributions. So on your formula sheet, we're in chapter 6 now. This gives us the formula. We know mu represents mean, which is saying the mean for variable x. What's this symbol mean? So add them all up, the sum of x times p of x. X is our value, p of x is the probability. So let's find the mean for this distribution. So I've given you a probability distribution. We have x, we have p of x. So what we need is one more column for x, p of x. So 0 times 0.06 is 0. 1 times 0.58 is 0.58. 2 times 0.22, 0.44. 3 times 0.10, 2.3. 4 times 0.03, 0.12. 5 times 0.01 is 0.05. Right, and then what do we have to do? Add them all up. So the mean is just adding up all the xp of x's. So we could get 1.49. Is that okay? The next slide, I put it on here because your book talks about it, but it's not really. I think I'm just gonna skip over this for now. If that's okay. I'm gonna talk about it later. What we really found here is if you think about your probabilities, that would be out of 100, right? So if we change this data and we translate our probabilities, this is like a 6% chance. So it would be like out of 100, I would get 0 6 times. And I would get 1 58 times. And I would get 2 22 times. And so it would be like adding up all 100 of those values and dividing by 100. That's really what we did for our mean. So it's kind of the same thing we've always done for an average. You add them all up, divide by the total. It's just, instead of writing 1 out 58 times, we take it times its probability. And then, since these were out of 100, using the decimal format means we don't have to divide by anything. So that's kind of why this formula works. Let's look at a big set. All right, so what if I wanted to do this? Could I make a probability distribution if I wanted to? Yeah. There's 100 values. So if I chose to do my probability distribution, what would we do? Start typing. If we wanted to make the table for the probability distribution, we'd have to list our x and the probability of each. And so we're looking, we have outcomes like 0, 1, 2, 3, 4, 5. And how would I find the probability of those? Count them, divide by 100, that gives me the probability. Is it worth our time to do this though? No, because what's the easier way to find this average? Add them all up and divide by 100. So we have the probability distribution option, but you don't have to make more work for yourself. You don't have to make a probability distribution just because we now have that. We can still use our old methods. So find this for me. So add up all these values. Probably be easier just to add up each column. 149 when you tie them all up. And when you get over 100 points, so we get a mean of 1.49. Okay, this is the extended data set from that. It was the same example. I just showed you two different ways of interpreting it. So this is where I had the probabilities. Example 6 is where I listed out all those individual points. And we just confirmed that we got the same mean for both. Alright. Mean can also be referred to as the expected value. So we've talked before, like if I'm rolling a dice, how many times would I expect, or what would be the probability of rolling a 4? 1/6. But if I roll it 6 times, does that mean I'm guaranteed to have gotten a single 4? No. But we know that the more I do it, the closer my probability will become to what I expect. So the mean of your distribution is called your expected value. And we know that as we have more trials, the closer and closer this will happen. So let's do a problem. It's going to ask me to find the expected value. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. The probability the female will survive the year is 0.99791. Compute the expected value of this policy to the insurance company. So when I see expected value, I'm asking you for the mean. This is what insurance companies do. This is how they determine how much you have to pay for your premium. They take into all the risk factors. They want to make sure they're going to be turning a profit in the end. And they have a method for calculating this. So if I'm trying to list my x and my p of x. Alright. My two options would be either she survives and they don't pay her, or she dies and they have to pay, right? So if she survives the year, does the insurance company make money or lose money? If she lives, they make money. It's life insurance. They only pay if she dies. So if she doesn't die, they get to keep their money, right? How much money did she pay them? So they would expect to have $530 if she lives. What's the probability that that happens? Okay, the other option, they have to pay. So how would I find that probability? So we get 0.00209. Okay, but in that scenario, if they have to pay out, how much money are they paying? $250,000. Now, they didn't lose all $250,000, right? Because she started the year by paying them $530. So the actual loss would be $250,000 minus the $530 she paid them. Okay, so they would really end up having to pay $249,470 out of their own pocket. And if they're paying that, we're finding the value to them, that would be a negative value. Would we agree with that? Okay, so the expected value is the mean. We have to take the x times p of x. And we're going to add those together. So So the mean, add those two numbers together. And and how much money are they expecting to keep? $7.50. Now, does that work if they insured 10 people? No, that's only going to work if they are insuring a large number of people. But remember, the mean, the expected value, is assuming for large values of n. So if they insured 100,000 people, they would expect to profit $7.50 for all 100,000 of those people. Does that make sense? The last piece I'm going to talk about is how to find standard deviation on this. And then I'll show you how we can use our calculator to do some of these things. So, standard deviation formula is a little ugly. So we know sigma means standard deviation. There's a couple variations. I think this one is a little bit nicer. So you have to add up x squared p of x, subtract the mean squared, and then we'll do the square root of that whole thing. So I want to do that for this problem. Give me a second, I'm going to go on to this. Alright, so we had the x and we had the p of x. The next thing we will need is an x squared p of x column. And you can do that a couple ways. You can take 0 squared times the probability, or you could take your x p of x times x again, and that would give you x squared, so 0 times 0 is still 0. 0.58 times 1 is 0.58. 0.44 times 2 is 0.88. 0.3 times 3 is 0.9. 0.48 and 0.25. So our standard deviation formula says it's the square root of the sum of the x squared p of x's minus the mean squared. So if we add all those up, we get 3.09. From example 5, what was the mean of this? I have the square root of 3.09 minus 1.49 squared. We get 0.9327 for the standard deviation. I also asked for variance. How do you find variance? So if I square that, I get 0.8532. Your variance will be slightly different depending on how many decimals you keep on your standard deviation. So if you had squared the original number, it would be a little bit different than squaring that rounded number. Everybody see how we got those? So let me show you how to do it on your calculator. If you go to your list, so if we just go to Stat Edit, okay, what I want you to do is enter your X values in L1 and your Y values in L2. So this is from the original table in example 5. So So the x is 0, 1, 2, 3, 4, 5. Everybody get those? Now we're going to go into one variable statistics. So stat, calculate one variable stats. The list is L1, but here's the new thing. The frequency, that's your probability. So that needs to be L2. So if you hit second and the number 2, that puts L2 as your frequency list. And then if we hit enter, X bar, the mean, was 1.49, which is what we got on example 5. The standard deviation, the sigma, 0.93268, so 0.9327. So same thing we got before. So we can do these on the calculator or by hand. You just have to make your probability the frequency when you do that. Did everybody get that on their calculator?
I did steal these from you. Do you want that box on the top for?
So that's all I have for today. So just a few. In terms of finding the mean and standard deviation, I like for you to do one by hand just so I know you can. You can use calculators for the others. 21 is a pretty small data set, so I would do that mean and standard deviation by hand, but like 18 is bigger, you can do that on your calculator.